Hello, and thank you for joining us for tonight's presentation, Energy in a Flash. We're pleased to offer this presentation in partnership with the U of A's Future Energy Systems program. My name is Colleen Elliott, and I am the Manager of Education and Special Events in the Office of Alumni Relations. I would like to acknowledge that my home here in Edmonton and the University of Alberta is located on Treaty 6 territory, and respect the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. The University of Alberta Alumni Association is a supportive, proud, global network of graduates collectively making extraordinary contributions to the alumni community, the university, and the public good. Part of our mission, as demonstrated tonight, is to connect, engage, and support alumni by providing lifelong learning opportunities for personal and professional growth. Before we start tonight, I have a few housekeeping notes. The presentations will be shown initially via a pre-recorded video, which is approximately 25 minutes in length. Afterwards, the researchers will join us for a live Q&A session. If you'd like to submit a question, put it into the Q&A box, which should appear in your toolbar at the bottom. If you open the Q&A box on your screen, you'll see all the questions that have been submitted live. Next to each question, you'll also see a thumb icon. If you see a question already posed that you're interested in as well, press that icon to upvote that particular question. The questions with the most upvotes move to the top, indicating that they're the most popular questions. It also saves you from having to type the question again. Our Zoom platform offers closed captioning. If you'd like to use this feature, please click the CC button on your toolbar. If you'd like to turn it off, press More and select Hide Subtitles. We would like to thank our affinity partners, TD Insurance, Manulife, and First Foundation, whose support makes events like these possible. Now it's my pleasure to formally introduce tonight's researchers. And they are a very bright group, so the introductions are considerable. Himani Pandey is a PhD candidate at the Department of Economics. She is working with Dr. Joseph Marchand, examining the future of energy in labor markets in Canada. She received her MSc in economics in India, and her dissertation focuses on the net effects of coal mining at a local level in India. Michael Moore received his bachelor's degree in mechanical engineering from Dublin University, Trinity College Dublin in Ireland, and his MSc in mechanical engineering from the U of A. He spent 2 years working at Intelligent Energy in the UK as a fuel cell research engineer. He is now a PhD candidate using numerical modeling to study polymer electrolyte membrane electrolysis. Bandita Dekka-Kalita is a PhD student in the Alberta School of Business. Her research is focused on institutional change in contentious sectors of society. She is currently studying such phenomena in the oil and gas sector of Alberta. Prior to coming to Edmonton, she served in the industry in various roles, and she holds degrees from the Asian Institute of Technology and Gauhati University. Dr. Musa Mogimi Haji received his PhD degree in energy systems from the University of Alberta. After a year of fellowship in the Electrical and Computer Engineering Department, he joined the Computing Science Department. His research interests include power distribution systems, analysis and control, application of artificial intelligence in power systems, and smart grid. Wenbei Zhang is an MSc student in the Department of Resource Economics and Environmental Sociology in AILS. Her research interests are resource economics and energy policy evaluation. She is currently investigating biofuel potentials in the framework of time series price analysis and geographic information systems for her thesis. With that, I think we're ready to begin our presentation. I hope you enjoy them, and we will see you in approximately 26 minutes.
Natural resources, particularly the non-renewable ones, are geographically concentrated and may have specific implications on the socioeconomic outcomes of the individuals living in regions abundant in such resources. Coal is an essential source of energy worldwide, feeding into several other industries and activities, making it no less valuable than gold, thus, black gold. It is a strategic resource for India as well. Hello, I'm Himani Pandey, a PhD candidate at the Department of Economics, and I am looking at the effect of coal mining on children's education in India. Coal mining activity in India is concentrated in central and eastern parts of the country. This provides us a natural setting to explore the trade-offs that families living in these regions face versus other regions of the country in terms of the schooling decisions they make for their children. Local economy in these mining regions presents the individuals and families with differing conditions in terms of labor market opportunities, environmental factors, and infrastructural setups. These could impact the schooling outcomes for children living in these regions who constantly are divided between going to school or going to work as child laborers. The objective in my research is to explore how the probability of a child living in coal districts of India to attend school is affected when exposed to the rising international coal prices. Using international coal price movements allows us to avoid any dependence on local factors or policies that may have an impact on education of children in a region. These prices are completely independent of local policies and institutions in India, but they significantly impact the local coal prices in India and are therefore an appropriate variable to compare the effect of coal mining activity in India on the education of children living in these regions versus regions with no active coal mines. The data from India suggests that between 1999 to 2011, the proportion of children attending school has increased from 69% to 89%, whereas the proportion of children working has declined from 28% to 9% respectively. A difference analysis allows us to explore whether this increase in schooling proportion can be attributed to the presence of mining activity in a region and by what magnitude. The results suggest that mining activity in a region indeed generates favorable outcomes for children in these regions by positively affecting the probability to attend school. When international coal prices double, the probability for a child to attend school in these regions increases significantly compared to children in regions with no coal mines by 4 to 5 percentage points. These positive outcomes can be understood through the interplay of the opposing positive income effects and negative substitution effects. Income effects are the positive effects in household spending when there's an increase in the real income in the economy. In this case, the positive pull in the local incomes comes due to the rising coal prices, which increases the economic activity in the mining region, generating more jobs and more incomes. The analysis suggests that families which have middle-level wealth witness significantly increased probability of school attendance for children, but very poor families are not able to benefit from the rising family incomes as much because they use it to meet the essential needs and still prefer the children to work for family income. Very rich families, on the other hand, are unaffected by these trade-offs as their children do not need to work for the additional family income at all. Substitution effects are the implied costs that one incurs on losing an opportunity, which in this case of schooling is the opportunity to work. Results suggest that when faced with increasing international coal prices, the households in coal districts of India do not prefer to send their children to work for additional income. This negatively affects the opportunity cost of education, thereby weakening the substitution effects. Given that the international coal prices significantly impact the domestic coal prices in India, they alter the local labor market conditions in these regional economies. Increased demand results in rising income levels in coal mining regions, and with limited impact of substitution effects, middle wealth families benefit immensely when exposed to the coal price rise internationally. These families can overcome the cost of education, direct and indirect, thus deciding to send their children to school. Therefore, natural resources, when sustainably mined, can generate positive outcomes at a local level and benefit the local economy and its people in various ways. This is important for developing nations where the abundant natural resources can be a source of growth and development for the local people. Thank you.
Hello, my name is Michael and I'm going to be discussing some of the work that me and my lab mate Manas Mandal are doing at the Energy Systems Design Lab as part of the Utility Scale Energy Storage project in FES. So why does FES have a project that is dedicated to energy storage? Well, to lessen the impact of climate change, it is projected that a huge increase in renewables will be needed over the next 30 years, particularly wind and solar. But large-scale deployment of these renewables is complicated by the intermittency of wind and solar energy. For example, on the 13th of May in 2018 in California, there was a lot of solar energy generated around noon, but not enough demand, leading to about 12 gigawatt hours of energy being lost or curtailed. So we would like a way of storing that curtailed energy and using it at other times. There are a number of solutions, depending on the scale, some of which we study in our lab. However, me and Manas focus on hydrogen. So why hydrogen? Well, the main benefit is that it's very flexible. It can help to decarbonize many sectors. It can also be stored at large scales for months, and it's already a $120 billion commodity today with about 80 million tons being produced each year, which will have to increase significantly to help mitigate global warming. Currently, hydrogen is made by reforming natural gas, which is a pretty big carbon dioxide emitter. Ideally, we would like to use renewable energy to do water electrolysis, that is, the splitting of water into hydrogen and oxygen. Now, there's a few ways of doing this, each with their own pros and cons and readiness level. However, we'll be focusing on PEM electrolysis, as this is the most popular technology, making up the majority of new electrolysis installations in recent years. It works by bringing water into the anode side of the electrolyzer cell. When it reaches the anode catalyst layer, a reaction occurs that splits the water into oxygen, protons, and electrons. The oxygen is typically vented, electrons travel through an external circuit to the other side of the cell, while the protons cross the polymer electrolyte membrane, aka the PEM, which separates the two sides and the hydrogen from the oxygen. The protons will recombine with the electrons to produce the hydrogen gas which we store. These devices are very expensive to make and run, however. We have to use iridium to split the water in the anode, as the conditions there are extremely harsh. And unfortunately, iridium is rarer and more expensive than platinum. The system is also quite inefficient. A lot of our energy from the renewables is wasted doing that water splitting in the anode catalyst layer. So people just tend to add a lot of iridium in there in the hope of getting good performance. So our work focuses on trying to better understand the anode catalyst layer and to try and reduce the amount of iridium that is needed. Manas did all the experimental work. The first step for him was developing a manufacturing process that gave good reproducible performance. The catalyst layer is only 4 microns thick, so it's made using an ink. Manas was the first to use inkjet printing to make them and was able to get a very good reproducible performance. Next, we wanted to characterize the anode catalyst layer so that we could use that information in numerical modeling. Manas was the first to measure the conductivity of the protonic phase and the electronic phase and show that the electronic conductivity is incredibly low and is much lower than the protonic. So the electronic conductivity is very low, but how do we know if this is important or not? Well, I do numerical modeling to find out. What we do is we take the part of the electrolyzer cell that we're interested in, which are the layers at the center of the cell, and we idealize this as a mesh. In each mesh element, we solve differential equations such as Ohm's law, which in this case will tell us what voltage the protons and the electrons are seeing, and this will depend on the conductivities that Manas measured. When we solve these equations, we get a map of what the voltages will look like. With this, we could do some post-processing to get a map of where that water splitting reaction is actually occurring. So we ran our model, and this is the polarization curve that we obtained, which is the main performance metric that is used. This curve shows the current on the x-axis. The higher the current, the more hydrogen we are producing. The y-axis is the voltage. The lower the voltage, the more efficiently our cell is running. But let's look at our map of the reaction in the anode catalyst layer when we are running at high currents and producing a lot of hydrogen. Yellow shows the high reaction rates, which is all at the left-hand side because of that very poor electronic conductivity. Most of the layer is actually purple, so it isn't actually catalyzing the reaction. It is actually just being wasted. So perhaps we can make a thinner layer which would reduce the amount of iridium catalyst that we use. Well, we simulated making the layer thinner and we actually got a slightly improved performance, but with 40 times less iridium than what we used to consider our standard. There is some experimental evidence for this in the literature for this performance increase with less iridium, and now our model can explain why this happens. So to conclude, hydrogen is going to be a big part of the climate solution, and we need to be making it renewably using water electrolysis. At the Energy Systems Design Lab, we have used both experimental and numerical methods to better understand what is happening inside the electrolyzer cell so that we can reduce the amount of iridium catalyst that is used. Thank you very much for listening.
In our research at the Alberta School of Business, we often adopt an organization theoretic perspective. In doing so, we aim to better understand social contexts and their implications on organization, management, and policy. My name is Pandita Teka Kalita, and today I'm sharing some interim findings from a process study with my supervisor, Joel Gaiman, on a transformation in the oil and gas sector of Alberta. The transformation we study is that of the organizing principles in the oil and gas sector. Also called institutional logics, these principles refer to the specific rules that inform that sector's practices, what actions they deem appropriate in that sector. For example, the appropriate practices in a family domain where the family logic prevails would differ from that in the market domain where the market logic prevails. We study how the logic of Alberta's oil and gas sector changed during the period between 1938 and 2019. Earlier, there was a focus on relentless profit-making, as exemplified by the image on your left of spectators watching oil explode from the Leduc No. 1 well in 1947. This extractive logic has undergone a sea change in more recent years. Companies are now more heavily scrutinized for their liability management efforts, as is indicated by the challenge of the orphan wells pictured to your right. To study how the logics transformed, we adopt a longitudinal and inductive research design. By longitudinal, I mean that our study covers an extended time period in which we observe regulatory practices during the respective tenures of 5 different regulatory agencies. By inductive, I mean drawing inferences from the data to build theory. Our data set consisted of interviews, archival documents, and observations. We analyzed these qualitative data using various methods, coding them into different categories such as time periods, meanings, organization types, etc. As we analyzed the data, we combined our emerging findings with theory from past work. The goal of this process is to develop new theory, that is, to move from specific observations in the data to broader generalizations about the phenomenon we study. So, what did we find? Well, we found that the process of logic transformation entailed 2 sub-processes. The first is a bottom-up process of evaluation, and the other was a top-down global institutional process. Let me briefly tell you about these processes. The bottom-up process of evaluation told us that logics transform as a result of a change in values. Discussions and debates around what constitutes or what counts as good and what organizational characteristics are worth holding in high regard showed us that people continuously reassess the question of worth or the question of what counts. We found multiple processes through which this collective assessment of worth took place across the decades. In the earlier extractive logic, these processes resulted in the prevalence of an indomitable spirit and a high regard for profit-making, whereas in the later period, this resulted in the prevalence of attributes such as accountability for your action and the inclusion of other stakeholders in consideration beyond simply profit-making. Top-down process of global institutionalization included the influence of cultural movements such as the environmental movement and other global events such as the Second World War and major economic downturns. For example, the problem of rampant bankruptcies arising from the oil price crash of 1980s led to companies leaving infrastructure on farmers' lands, and this put a spotlight on the cleanup issue. Apart from some key theoretical contributions to organization and management theory, we believe that by offering a processual understanding of change, our study can significantly help orient energy policy and organizational decisions in more effective directions. After all, any talk of future energy systems cannot be separated from the more substantive processes animating the societies these are intended to serve. Thank you very much.
Hello, my name is Musa Mugimi, and I'm a postdoctoral fellow at the Sustainable Computing Research Group at the Computing Science Department of the University of Alberta. Today, I'm going to talk about our research on voltage regulation techniques in modern distribution systems. With growing concerns about global warming, we are seeing many new technologies being installed in the distribution systems, from smart meters and other measurement devices to renewable energy sources like rooftop photovoltaic installations, or to new electrical loads like electric vehicles, which all contribute to reducing fossil fuel consumption. To take advantage of all of these technologies and at the same time ensure safe and secure operation of the electrical grid, we need to have proper controls in place. And proper control starts with proper monitoring, which is why we started our research with studying different state estimation techniques that enable proper monitoring and control of the distribution systems. But there's more studies to do. With all the benefits that come with PVs and electrical vehicles come a lot of challenges. For example, consider an electrical distribution system that has many PV installations. Ideally, we want the voltage level to always stay within certain limits. That is safe for the consumers, the appliances, and for the grid equipment. But we see that around noon, we have some over voltages, which is caused by the extra PV generation. Also, we see some voltage violations in the evening, and the voltage goes below the allowed limit here due to the increase in the electrical load demand and the decrease in the PV generation. I should add that having additional electrical loads like electric vehicles make these matters worse. And I also should mention that traditional distribution systems have some methods to deal with these voltage violations, but they are not simply enough to address all of the problems introduced by these PV and EVs. But that's not all the problem. All of the EV owners typically want to charge up their vehicle right after they get home in the evening. So many of these vehicles demand charge power at the evening hours at the same time. And I should mention that a single electric vehicle can derive power equivalent to several homes. So it's easy to see that such high demand can cause overloadings for transformers and transmission lines, and eventually can damage equipment. To solve this problem, we rely on scheduling the electric vehicle chargings using reinforcement learning techniques. And we try to efficiently use the maximum capacity of the grid without causing any voltage violation problems or any overloadings. At the same time, ensure that the maximum possible power is delivered to the electric vehicles. To deal with the voltage rise problems in the distribution system caused by the PV installations, we rely on energy storage units or batteries. So the idea is pretty simple. We want to charge up the batteries around noon when we have extra solar generation available, and in the evening we can discharge these batteries and inject this extra power or extra stored energy back to the grid when the PV generation is at its minimum or is non-existent, but the load demand is at its peak. So in this way we can fix the discrepancy between the solar generation and the electrical demand. Sample results show that we can effectively regulate the voltage using these distributed batteries. And I should mention that we want to have a method that is distributed and preserves the privacy of the consumers and scales well for larger systems with many PV installations. Okay, that was my presentation. I hope it was informative, and I would be happy to take any questions. Thank you.
Hello everyone, my name is Wenbei Zhang. I'm a graduate student from University of Alberta, and I'm working with a biofuel project team led by Professors Marty Luker and Wen Qiu. You may be wondering how a study of prices could possibly be interesting or relevant to you. In addition to being the amount that you have to pay, prices are important to the way that economies function. During the COVID-19 pandemic, demand for air travel and jet fuel dropped a lot, but diesel fuel trucks to deliver food remained important. Crude oil is currently a key input for making conventional jet fuel and diesel. Meanwhile, to reduce greenhouse gas emissions, new technologies are trying to substitute the biomass for crude oil to make biojet and biodiesel. This analysis investigates current price relationships between crude oil, jet fuel, and diesel, and we could use this information to assist the development of the emerging biofuel industry. To investigate these price relationships, I estimate what's known as co-integration models to identify long-run price co-movements over decades for the short-run price adjustments within weeks. We employ nonlinear error correction models. Nonlinear models allow for different price responses in alternative states, rather than linear models, which only allow for a constant price response. As jet fuel and diesel industries have differential price responses to oil price increases versus decreases due to specific market structures, nonlinear models provide better insights. My analysis uses a US price dataset from 2000 to 2019, and this plot visualizes the three price series: diesel, jet fuel, and crude oil from top to bottom. Prices tend to fluctuate a lot and move up and down together over time, showing that jet fuel and diesel prices are affected by oil markets in the long term. Jet fuel and diesel prices are affected in the short term as well, but in different ways, depending on whether oil prices are relatively increasing or decreasing. For jet fuel, we can see two potential states in terms of price changes of crude oil relative to jet fuel. State 1 is when oil prices relatively increase, which leads to response 1 where jet fuel prices do not respond in the short run. State 2 is when oil prices relatively decrease and jet fuel prices do respond. Why is the difference? It could be due to pricing strategies of jet fuel producers to their price-sensitive consumers like airlines and their passengers. They could also use hedging strategies to manage unfavorable oil price changes. Diesel prices respond differently. In the short run, diesel prices only respond to oil price increases relative to diesel prices. You might have seen this in daily life. This is because diesel producers could exercise market power over dispersed consumers. Think about the COVID situation when public health has been seriously threatened. People considerably travel less, but still rely on diesel to deliver food. In a word, jet fuel consumption is relatively optional, while diesel is essential. My findings are important for producers and policymakers. Governments are considering what types of incentives jet fuel and diesel producers have for using bio feedstock to diversify fuel production away from fossil fuels. My results about jet fuel and diesel's vulnerability to oil prices show how important this diversification could be. It could improve the ability of emerging industries to mitigate price risks from crude oil shocks. Moreover, given that jet fuel prices are more vulnerable to oil price changes than diesel, biojet may be especially attractive to jet fuel producers. So you see, understanding price relationships is important, not only because you and I have to pay these prices, but also because they are affecting the direction that the economy might go in response to climate change. Thank you.
Okay, I want to thank our researchers for their presentations. There are obviously lots of ideas and concepts in there to discuss. So we'll now move to the Q&A session. Again, the Q&A box is open and there is the thumbs up icon. If you see a question that you would like to have answered as well, simply click on that and it will upvote that question. To moderate this portion of the evening, we're joined by two members of the Future Energy Systems team. I'd like to invite Valerie Miller and Catherine Tays to join us. So Valerie Miller graduated from the U of A with a PhD in land reclamation in 2019. She is the outreach and engagement coordinator for the Future Energy Systems team. And Catherine Tays is the research communications coordinator, and she holds a PhD from the U of A as well. Welcome to both of you, and thank you for moderating this portion of the evening.
Thank you so much for having us. We're very excited to help get all of your questions across to our speakers. I will ask all of our speakers to join us on camera now. And we will do our best to get through as many questions that were submitted in advance and tonight. The first question, we're going to jump right in. It is a group question. What is the biggest challenge facing our energy system, and where do you think we have the most potential? Michael, do you want to start? Your mic is on.
Okay, yeah, sure. So hello, everybody, and I hope you found the presentation interesting. So the question is, where's the biggest opportunity, I suppose, and what the biggest issue is? And yeah, it's kind of tricky. I think the biggest issue that we have in terms of an energy transition is the fact that oil and gas is just a wondrous material. From an engineering point of view, it's amazing. It's so much energy, all very concentrated in a small volume and mass, which is quite difficult to create. And somebody's asked me to shut my mic. Sorry, that's about as much as I could do, I think. Can you hear me okay? Yeah, okay. So yeah, so that's the biggest issue, is that it's just simply very hard to replace something that has powered our civilization to some extent for a few decades, if not centuries. So that is the biggest issue. How do we overcome something that works so well? And obviously the opportunity that we have, I think, is that we're trying to replace this giant carbon-based economy, and we have an opportunity to replace it maybe with lots of different kinds of technologies and lots of different kinds of ideas, and we could be very smart about how we deploy lots of different kinds of technologies, and hopefully they can all interact with each other quite well. And hopefully, yeah, we can, for PhD students, there's lots of opportunities for us to come in and do some research and go out into the field and work in all these very new industries. And yeah, hopefully we can do something cool with that. So yeah, that's how I would think about it. Is just there's a lot of opportunity because there's so many different things we can do, and that we have to do really to replace oil and gas. Yeah.
I'll have a go at it. I think from an organizational perspective as well, there's lots of opportunity because as we found in our research, It's not only valuation and the value that we see that matters, but also how that value came about or how evaluation is done. And that is reflected in a large extent to the various practices that these organizations are following and the way that these practices have changed. And I think changing practices in a way can give us many different avenues to look at the future of energy and to look at the way things will go going forward. So that, I will say, is also an opportunity.
Thank you so much.
I also would like to add something real quick here. Like, I totally agree with what Michael said regarding like the major problem is that we have this like huge, I'm specifically talking about like power systems in general, including like power plants, transmission system, distribution system. So all of these, this huge system is designed to last like for many decades. And now it doesn't make economic sense to like suddenly shut down everything and make everything renewable. However, we have to notice that like the electrical load is always like growing. Like it has been like this for many years, and it kind of makes sense. So, and another point is that, so like eventually like you have to add extra transmission capacity, maybe extra power plants. And another important point is that they do all of these studies, like when they want to like design how much transmission capacity is required, they do everything based on peak load. So for the most part of the day, the load is kind of like close to the like base load or an average amount. But like especially for like the residential sector, we see these huge peaks in the evening hours, for example. Depending on the area, the time would change, but in general, we will have peaks, and we have to be ready for this. So eventually, the current network would not be enough. We have to like install extra capacity, which is extremely costly. And traditionally, this peak load is met by like smaller power plants, which are pretty quick to like start up and shut down, and which are more expensive to run compared to the huge power plants that are used to like supply the base load. So this is where the renewable energy and like bad energy storage systems could come in, because they are pretty fast. And if we have enough capacity to just shove that peak and make everything smooth, we can take the best out of our current energy systems. There's a lot of cost savings involved and a lot of like reduction in carbon emission.
Thank you so much, everyone. Anyone else have any things they want to add to that question, or shall we move on?
Yeah, I can say something from the perspective of my research. So I think the biggest challenge in our energy system is financial viability of the alternative fuels. And as for potentials, it could be intensified regulations that promote transition to low carbon economy. And there are more and more supportive policy for developing biofuel. And also, based on my research, one opportunity stems from volatile petroleum product prices, and the biofuel has the economic benefits to mitigate vulnerability to oil price shocks. Yeah, that's it.
Thank you so much. All right, let's keep going with these questions. Himani, do you think that your findings in India could be applicable to other regions of the world for other resources?
Hi everyone. Yeah, with respect to your question, for sure, actually, These findings that I've had for India, and like India is a developing nation which is abundant in these kind of natural resources, and it is heavily reliant on these kind of non-renewable sources for its energy requirements. And that is a scenario in almost so many other developing nations also around the world. I know a lot of developed nations are now moving towards more renewable sources, but the developing nations are still relying on those non-renewable ones. So wherever I would believe that you have a labor intensive industry, it's like an industrial activity that I've actually captured, the mining activity in India. So wherever you could find such kind of an industrial activity, you would be able to replicate these kind of results or do similar kind of analysis to maybe finding a different outcome out of it, but then the analysis could definitely be replicated, because I'm treating this like an industrial activity which is highly labor intensive, bringing about labor market changes. So that is how I'm addressing the problem. So I do believe that it could be seen in other parts of the world too.
I think it's really interesting that you bring up the idea of labor markets, because somewhere like Canada, for instance, has a much lower population density. Do you think that that's an important aspect of your research as well?
Absolutely, yeah. When we talk about Alberta or Canada, it's going to be very different from any other economy where the population density, as you speak, is going to be pretty high, or where a lot of the labor force is going to be dependent on certain kind of industrial activities for their livelihoods. We do see some kind of these trends in Alberta as well, because Alberta is also to some extent heavily reliant on energy, on oil, as we've always known. And so we do see that, when there are boom and bust cycles, it does affect when there are prices going up or down and crashing. It does affect the economy in several ways. And that is all because of the way the labor market is going, getting affected. So the magnitude is definitely smaller here. It's definitely very protected out here. It's not as protected outside, Canada, around the world. And they are not immune to those kind of shocks. And some countries do not perform that well. Some regions, I would say, do not perform that well, but there are certain regions who do perform very well, even when exposed to those price shocks. The idea is that, if you're relying on some kind of an energy, we know that you want to, go away from this energy source to some renewable form of energy or a more cleaner source of energy. But if you do not have much options available and you have a huge population to support, how well can you use it, or how sustainably can you use it for the benefit of your population? And that is the whole idea.
Yeah, thank you. And I do really think that it's interesting to talk about the transferability of this kind of theoretical work that we do sometimes at the university. And I'm going to pose the question actually to Wenbei and Bandita. Similarly to Himani, do you think that your findings are transferable to other sectors or other countries? And I see Bandita nodding along, so I'll pass the question to you first, if you don't mind.
Sure. So with respect to our study, it can definitely be replicated across other contexts. Our findings are still emerging, but at this point, we can say that they are definitely replicable to sectors that depend on extractive practices, such as coal and timber, for example, because some of the mechanisms that we theorize about are based on such material resources. We also have come across some very interesting mechanisms that are based on emotional stakes attached to such resources, and what role those stakes can have in long-term transformations. But I think at this point, even beyond such research, such resource-related contexts, our theory of evaluations can actually be extended to any field which is susceptible to change. And given the times that we're living in, it might be safe to say that that probably includes just about any context where there are organizations. I'll just go out on a limb and say that. But as I said, our findings are still emerging, so they can definitely be replicated. Yeah.
Yeah, we definitely live in changing times. Wenbei, do you want to add anything to the question?
My analysis tools is definitely replicable to other data in other contexts of different countries and the different product prices. And actually the So nonlinear modeling is quite flexible, and it allows for different kinds of price relationships as long as we obtain good data and use appropriate analysis tools. Yeah, that's it.
Okay. I'd also like to add to the transferability part that, I was discussing that with respect to the non-renewable resources and the developing nations, my results are pretty much, replicable, and we could find out what happens to other regions around the world. But even if it comes to other sectors, this analysis is very much replicable or transferable in the manner that it's an industrial activity. And if you're setting up any kind of an, generation of energy or electricity from a renewable source or any other source of energy as well, you could apply the same methods. And that is the best part of the research, that the methods are definitely replicable. The outcomes would vary. And that is what research is all about. We get to see how the outcomes are, but the methods are absolutely replicable. Thanks.
Thank you all so much. It's such an interesting conversation seeing how connected all of our research is. Next question is for Michael. Can the currently installed solar systems possibly be used to integrate with hydrogen electrolysis systems, or is an entirely different or new installation required?
Yeah, so this I don't know a huge amount about, but as far as I'm aware, the idea would be that all of our solar energy and all of our wind turbines, their primary purpose really is to go into the grid. So everything will be going into the grid to hopefully go directly to homes and to businesses, and that would be the most efficient use of that electricity. So when it comes to electrolysis and generating hydrogen, it's really to do kind of what Musa was talking about, where you take these peak loads or peak supply, I guess, of electricity from these renewable sources, and you use that to generate hydrogen. And I think that would probably draw it straight down from the grid. I'd be surprised if they did it any other way. With one exception being if you are in a location where you have a lot of supply of renewable resource, but you don't have a lot of demand. And like a place that people talk about a lot might be Northern Africa, where you could have enormous solar farms and be producing vast amounts of energy, but there's not the local demand there because there isn't sufficient industry and etc. So then how can you take advantage of this? So one thing you can do is try to build like very high voltage, massive, I guess, electricity cables to try and get it into Europe, into Northern Europe. That would be great. But people are trying to figure out what are the economics of just hooking it up to an electrolyzer, producing hydrogen and transporting a molecule instead. Perhaps that is a more economically viable way of taking advantage of a big natural energy resource. And because the problem is that hydrogen is unfortunately quite difficult to transport. So there's all sorts of considerations that have to be taken into account there. People talk about, maybe making ammonia factories in Northern Africa, this kind of thing. So yeah, but yeah, I think in general, the idea would be to make renewable energy resources, have them close to demand centers, and then to use electrolysis systems or other systems such as batteries to get that oversupply that we often see. So that would be, I expect how most electrolysis systems would be used. Yeah.
Yeah, I think that's a really salient point for a lot of research in renewable energy sources is how do we get the renewables to work well with the storage so that we have the power we want when we want it. And there's lots of different ways that we're looking at that. So I'm actually going to turn the question over to Musa, because you also mentioned similar issues surrounding solar power and storage, though probably a different kind of storage than Michael is discussing here. How much storage capacity did you consider in your analysis of this kind of optimal grid? And is it mostly, traditional batteries that we're used to? And how much does new technology like Michael's affect the kind of analyses that you're doing?
Actually, like my study, I I just considered battery energy storage systems. So that's that. But like, there's not a specific answer on how much we could use. Like, it all depends on your load characteristics, how much like solar installation you have, like the season, the area, like all of these factors come in. But the important thing is the whole idea that like we are able to shift this peak load, and that is where like good things happen. And that's not the only thing, actually. Like, there are a lot of studies, like I didn't take that approach, but there are lots of researchers like trying to like consider application of these like energy storage systems for other things, like frequency like control, like other stuff, many other stuff that are traditionally done via like power plants, like some mechanisms in like traditional power plants. People are investigating the possibility of like using all of this like applied capacity, especially when we have enough installations. Like, as low installation, honestly, like you could do some stuff, right? Still like energy storage for like load shaving or local voltage control. But once we have like a lot of this capacity installed, now we can do more and more. Like, it's a gradual thing. But yeah, new types of batteries definitely help. Like more efficiency definitely helps. Like more power definitely helps. If we could have like in the same footprint, if we could store more energy, that's gonna definitely help. So everything like could contribute.
And I think that leads really well into a question we actually have from the audience in the Q&A box here, directed at Michael, but I think Musa, you might have some interesting insight into this as well. How fast do you think practically the development of energy storage, or potentially Musa in your case, these kind of old technologies that we're improving, how fast is that development to keep up with the increasing renewable energy inputs that we have into the system? Or in other words, I guess, how far is that research from commercialization and integration into our systems?
I think Michael could answer this question better, but the thing is, like, it's not like if we don't have energy storage, we cannot take advantage of like renewable energy. We can still like have a lot of benefits from them. The thing is, if we could have energy storage, things are even better.
Yeah, for sure. I mean, the problem is that we have this impending sort of issue of climate change, and how are we going to deal with that? But really what is still the most important point at the moment is the economics, unfortunately. So it has to be economical. So I think the way things are at the moment is that we have relatively small renewable energy penetration into the market. So things like batteries are more viable, which is why you see, that big Tesla battery in Australia, for example, which is doing extremely well, but it's only really doing this load shaving. It's about frequency regulation. So it's kind of a very short-term modulation, I guess, or control of renewable resources. And yeah, in order to really take advantage of renewable energy resources, we do need to get into very large scale storage. And that has to become a lot cheaper, unfortunately. So I think projections right now is that green electrolysis, which is using renewable energy resources, put it into electrolyzer, like a PEM electrolyzer, to produce green hydrogen. That costs somewhere between $4 to $6, $8, even $10 per kilogram. These are the kind of numbers that are thrown around. I think it varies quite a bit depending on the local resource. And yeah, there's a lot of factors, I think, in there. But to compete with hydrogen prices at the moment, in terms of I think it's called gray hydrogen maybe, or brown hydrogen, which is hydrogen produced from natural gas, you're talking about $1 per kilogram. So we have to have this very large reduction in price. And that is going to take some time. I think projections from the Atomic Energy Agency, or the International, what is that, the IEA? International Energy Agency, they're talking about maybe by 2030, that green hydrogen can be cost competitive with, I think it's blue hydrogen, which is hydrogen that's produced from natural gas for carbon capture and storage, right? And that's going to be coming in at around $2, maybe $1.50 per kilogram. So that's kind of the cost reduction that we have to achieve. And that, it does take some time, but fortunately the learning curves that we're seeing for hydrogen production in renewable energies is quite high. People are saying it's somewhat similar to what we've seen from solar panels. And by learning curve, I mean that we've, the more you produce these things, the quicker the price comes down. And so solar, for example, has seen very, very large or very rapid learning curves, which means the prices reduce very, very quickly. So people are optimistic that we can actually achieve these targets, and we could start to really ramp up hydrogen production, start to make, which makes it then easier to justify very, very large solar arrays and wind turbine farms, and everything becomes a lot easier when the price goes down. But we're not there yet, unfortunately, and there are big challenges to overcome. And yeah, so it's going to be interesting to see how it goes. Yeah. But for now, I suspect that we'll see relative, like smallish renewable energy deployment with batteries to do the control of the demand. So maybe 2030 to 2040, we'll see a lot more hydrogen, I suspect. Yeah.
I'll just actually follow that up with a kind of a related question from the chat here, is asking about the studies on the relative economics of the various colors of hydrogen, which is why I'm bringing it up now, as you've kind of approached the subject yourself, versus natural gas versus diesel. The relative economics, if you break it down to, dollars per kilometer driven, do those kinds of studies exist already?
I'm sure there are plenty of studies like that. I couldn't really say. So, but I think the question is maybe specific about the use of hydrogen in cars, I believe, right? If we're talking about dollars per kilometer driven. And yeah, there are studies on that, trying to figure out, that would be nice that you can power your car with a solar panel, via hydrogen electricity. That would be quite cool. But I don't think, at least the people that I listen to, podcasts, whatever, they seem to think that hydrogen will not be that big for transportation, not on the level of passenger cars, maybe not even heavy duty trucks. So they feel that batteries will be more economical in that case, right? The problem with the hydrogen energy vector is that there's still quite large inefficiencies. So you would take your solar panel, you would produce energy, you would produce hydrogen, and there might be a 60-70% efficiency there. And then you'd put that into a fuel cell, which will convert that hydrogen energy into electricity in your car to drive the electric motor. And there's another 60-odd% efficiency there. So you would lose quite a lot of that energy from your solar panel. But batteries, of course, that energy efficiency will be closer to like 90%. Right, so people are just looking at those kind of numbers and saying, yeah, we expect that hydrogen will not be used for that kind of transport. Maybe more like large scale marine, like shipping, or like aviation, perhaps. We could see hydrogen being used there. But yeah, I couldn't really talk about the economics of the transport part of it, unfortunately. Yeah.
Thank you for your answer. And I see this sashaying a little bit towards Wenbei's area of expertise in terms of the economics of fuels for transport. Wenbei, I wonder if you have any comments on, different colors of hydrogen exist, but different types of biofuels exist as well. Primary or tertiary biofuels. I wonder if you could comment on if those play a role at all in, Canada's ability to make biofuel, or the price that biofuel would cost consumers.
Sounds a lot of questions. So the first question is that how much biofuel can Canada produce, right? Or
Yeah. I guess the question is, what's Canada's potential for biofuels? And, there's a lot of concern about the cost of biofuel because it takes up agricultural land. So I wonder if you
Yeah.
could comment on that a little bit.
In terms of the impacts on land use due to biofuel production, in the literature, people usually divide it into two pathways. One is called direct land use impact, and the other is indirect land use impact. Specifically, the direct land use means the direct land use impact means more land will be diversified to biofuel production, and definitely the cropland for crop production will decrease, and the indirect land use impact is also known as displacement effect, because as the food prices increases due to maintain the enough food supply, farmers will use more land, probably primary land, to produce crops, and it will increase more cropland. And yeah, and can you say it again? Another question is that?
I think you addressed parts of it throughout your answer. So I think we have potentially a group question, Valerie, from the audience.
Absolutely. So there has been a lot of discussion around renewable energy and all of these different technologies, but not a lot of discussion about life cycle of these technologies during production and then cleanup at the end, reclamation, and what do we do with the materials? Can anyone speak to the life cycle issues around different energy? Or even if we're thinking, Himani, with your research related to coal and education, also the environmental effects. So if you want to start, and then we'll pass it around.
Sure. All right. Yeah. So I'm addressing coal. So with that, I know comes a lot of environmental effects, and I think we're all very much aware of it. The amount of carbon footprint leaves and the kind of pollution-related damages it is particularly causing. There are lots of studies out there when you talk about the resource that I'm working with, non-renewable resource in particular, to discuss how environmentally bad it could be and affecting the health outcomes for individuals, and that too affecting, like I've explored in my paper, how coal mining is affecting the educational choices for individuals in India. And if this was routed via the pollution, there are ample studies out there which discuss that, when you have such kind of an activity in your vicinity, because of the environmental damages, because of the toxic materials present around you, the cognitive skills of the children, they actually get suffered. At the same time, their health gets suffered. So this could actually go in the other direction as well. And which is why I say that, they have to be used sustainably. We have to understand that, there are certain kind of benefits also that you can acquire when you're at a local economy, because you need to have certain amount of these kind of resources also, because you have not completely transformed to the other sector. You're still working on developing the other parts of the energy systems in your economy. And if you have to rely on this one, then you particularly would have to understand that there are those kind of damages that are there, and those are the costs. And I've tried to address that a little bit in my paper, the environmental costs that are there. Because of the environmental costs, I've actually addressed that because coal mining affects the landscape of the the local economy, it would be affecting how children would be accessing schools, and whether they will be how is their educational outcomes faring up because of that. So I've addressed those in my regressions also. And I've just said that, despite those things, if I use my resources sustainably through the labor market benefits that we're generating, we could see that, some children are still able to go to school because they were previously not attending school. And it gets beneficial in cases like India, which is a developing country where children were not attending school. And now with this labor market impetuous, they can actually do so, despite the fact that, yes, there are environmental damages and the governments are trying to correct for it. The companies itself are trying to correct for it. They're trying to, address those concerns. When they're dumping the waste, they're trying to, environmentally maintain it also, so that, the pollution impacts are pretty low. So that's what I've seen from my resource. But I know for the renewable ones as well, there are lots of studies out there which talk about how the generation happens and how it affects how the waste material gets tackled. There are studies out there, but yeah, I'm not an expert. So I believe the others could highlight.
It is looking at all of those different parts of the chain. Who would like to go next? Wenbei, your mic is on. Do you want to touch on the life cycle of materials? Michael? Wenbei or Musa, your thumbs up. Awesome.
Yeah, I can go next. So actually, regarding the life cycle, we have different life cycles, right? For solar panels, it's typically 30 years or so. And for batteries, I know that for Tesla batteries, Tesla Powerwall, for example, they start to lose some capacity at 10 years old, and after that, it's not it's totally unusable. It's not as efficient, or the capacity starts to degrade. But they will last for a few more years probably. So, but the other thing is that the traditional power plants are also have do also have a life cycle, right? Which is in the range of 30, 40 years. So, which is pretty comparable with the solar panels, right? And another thing is that the major difference is that we see the solar panels, right? So we think about that, oh, what's going to happen after this one doesn't work anymore? But we don't see the other one because it's probably 200 kilometers away. We don't see that. So everything is fine, right? And so that's that. And also, one thing that I feel that is missing from the argument is that renewable energies are not just solar and wind, but majorly nowadays when people talk about renewables, we just talk about wind and solar, but hydropower has been in use forever, and it is technically renewable. It's very clean, it's very efficient, but the problem is that you cannot have hydro everywhere, right? Places that do have hydro are super lucky, right? It's free, it's there, it's clean. I know that some provinces, some Canadian provinces, Quebec has 95% power from hydro, which is pretty great. They have 4% from wind, I guess. And then BC has 85% from hydro. But again, the problem is that, for example, in Alberta, there's not much places to install a hydro plant, right? But regardless, back to the question, all of these technologies have a life cycle, and at some point they have to even coal power plants or oil gas power plants, at some point they need to retire, right? It doesn't make sense to run them anymore. The maintenance costs and everything else just goes beyond the point that it makes sense, right? So yeah, it doesn't renewables don't have to be perfect. They just need to be comparable or maybe a little bit better than the traditional technologies in regards of the life cycle and the recyclability. I don't know, that stuff.
Right, there's definitely a variability, and I think certainly I was surprised when I first learned that Canada is over 60% powered by hydropower. So it's something that you're not necessarily aware of until you start looking into it. Michael, I see your mic is off. Would you like to comment on potentially hydrogen power?
Yeah, for sure. Because
there's some quite interesting issues when it comes to renewable energies and life cycles, and that is like the materials that we use are often very, very scarce and quite expensive. And that's going to be a very big problem in lots of different parts of the renewable energy process. Like I'm not sure in wind turbines and solar panels, but there are certainly issues in turbines, I think, with certain components of the turbine that use very rare earth metals, and they have to be, they are expensive, and recycling is going to be a very, very important part of the renewable energy transition in order to be able to recover these expensive elements. Like for batteries, cobalt is an issue, I think. It's quite rare. And for me, with the hydrogen economy, we use platinum on one side of the cell that we have. The catalyst that catalyzes the hydrogen reaction actually uses platinum. The one that catalyzes the oxygen reaction is iridium. And both of these are quite scarce. And to give you an idea of how scarce, like people don't actually mine for iridium. They mine for platinum, and if they find some iridium, then they are very happy. Happy days, they've gotten this very expensive material. And we need quite a lot of iridium to make our electrolyzers. So, and it's quite tricky, unfortunately, with electrolysis because it's a very, very corrosive environment. Durability is a very big issue. We don't have very long life cycles for PEM electrolysis at the moment, not unless you use lots and lots of this catalyst. So what's going to be very important going forward is that we can build these electrolyzers, that we can run them to a reasonable lifetime. Like people are aiming for 10,000 hours, which I think might only be maybe 5 years or something like that, when taking into account the capacity. And yeah, and once it comes to the end of its life, we have to be able to recover it, to recover as much of that iridium as possible and to recycle it, put it into the next one. And yeah, it gets quite interesting when you think about the materials choices in some of these technologies. For example, I saw a paper quite recently that was looking at asteroid mining and how that could be used to help boost renewable energy deployment, because you could, bring an asteroid from somewhere and mine all the precious metals out of it, So that just gives you a sense of kind of how important these materials are, how rare they are, and really how important our research is going to be to try and maximize the use of these materials. So
yeah, certainly I think it's extremely important to be thinking about the longevity of the technologies that we're generating. But we have actually an interesting situation in Alberta that I'd like to potentially invite Bandita to comment on in terms of the legacies of the past and current energy systems. We I think have been hearing in the news a lot more about abandoned oil wells as a consequence of our reliance on hydrocarbons. And Bandita, I think you have some experience in abandoned oil wells that I would invite you to share with us.
Yeah, absolutely. Thanks. I think this question, although it's specifically about life cycles of renewable energy, but I think, this issue of life cycle management and understanding the long-term implications of things and responsibly working towards that is really important. And as you mentioned, the problem of inactive wells, orphaned wells, abandoned wells that we see all around almost in Alberta is just so pertinent at the moment. And most of this, and our research has shown that most of this really has to do with what kind of processes and what kind of evaluation mechanisms really let you value one thing at one point in time and another thing at another point in time. And it is important, I think, to take that perspective, to take that substantive perspective and look at that in order that our policies can be effectively informed with such insights. And I, since I have the floor, I'll also sort of touch upon a question that I saw in the live chat box about the extractive logic and whether with our research we see that the extractive logic or the value of profitability and its its importance in the return on investment is going to go away, or it's not going to be there anymore. And our answer, our findings from the research is that that's absolutely not the case. It will be there, but then profitability or profits are not going to be the only thing that will drive competitiveness among organizations. You will need to manage your stakeholders. You will need to understand the implications on the environment, on broader stakeholders and broader society. As these various concerns keep emerging, your organization needs to keep up with that and needs to, and that really is what the change in logic is about. So just wanted to touch upon that as well.
Thank you so much for touching on that. I can say, even just in my small area of land reclamation, we can see over the years it started with everything just must be green. And now it is much more focused on incorporating communities and building biodiversity into our ecosystem. So we can see that role changing over time, what has value. Wonderful. We are running out of time. So we have a question for Musa, and then 2 group questions to wrap us up. So Musa, when will Alberta or Canada explore using electric storage of EVs as part of the power grid to manage local voltage fluctuations? Any perspectives on that?
With current technology, I think it will take quite a few years, because with the current capacity and the thing with voltage is that it's pretty local. So it's not like for other things, you could transfer power from BC to Alberta, no problem. There are some losses involved, but that could work. But for voltage support, you need to have local resources, right? So it's a pretty local thing. So it's you cannot support the neighboring provinces. So every province should have first enough EV cars available. Second, there's a infrastructure involved, right? With the smart chargers have to be in place so that they could contribute. That's why this is more on the research side currently, because and it makes sense that it has to be on the research side, because research has to be a few steps ahead of the current technology, right? So yeah, my research is more on the theoretical side. I don't see in the next few years that we could really apply these methods, but I know that they are running some experiments, at least for scheduling electric vehicle charging in the US, in the Europe. I know several real experimental results are running right now, which is good. Some universities are involved with the at least university parking lots. So it's going.
It's coming, but there's lots more to go. Yeah.
Yeah.
Awesome. Okay, group question. You're each going to get about 30 seconds to answer, because we have one last inspiring one after this. Do you think we'll ever shift away from oil and gas 100% to meet all of our residential, transportation, manufacturing, industry needs? Do you think that nuclear is going to play a role? Future Energy Systems isn't a focus, doesn't have a nuclear energy focus, but what are your thoughts? We're just going to go round table, quick answers. Himani, you're first.
I'll say why not, actually. Why shouldn't you? Given the kind of, the constraints that we have with the non-renewable resources, and we're just trying to make our way around them, that, how they can be beneficial to the local communities. We're always just running around the corners. That's not the answer. We all know about it. So the idea is to move away from them. And that is why I've also mentioned my research that we need to mine them sustainably. So that what always has to come in. So the idea is that you can't completely be dependent upon them, because there are costs and we want to really avoid those costs. So the idea is that we can move towards it. And yes, nuclear energy could be the way. Of course, it's going to be very cost effective if developed properly. I think so.
Thank you so much. Wenbei.
Yeah, I think when will we shift from oil and gas to green energy? This depends on manufacturers technology and the availability and feasibility of appropriate feedstocks for producing those green energy. And another factor is public acceptance. Although some feedstock is feasible, but the public have some different opinions, like the concern for food and versus fuel. And
absolutely, that's the importance of events like this, is really engaging with people. Thank you so much. Musa, you are next on my screen.
Okay, like regarding nuclear, yes, definitely it could play a huge role. Like right now, Ontario is doing like 60% nuclear, so it could help a lot in not using oil or coal. But the other thing is that I don't think we have to go to 0%. Like this is my personal like opinion. So I haven't done like any specific research on this, but I think it just needs to go like small enough, not exactly 0%, because there are a lot of like complications, majorly like for developing countries. It's going to be like crucial. Like they cannot go to 0%, at least for the next like few decades, because like they have invested a lot in the like power plants, like it's like oil, gas, whatever. So it's not going to work that way. But like it should start from the more developed countries. They should, and everything needs to go down to a certain level. In my opinion, it doesn't have to be necessarily 0.
Absolutely. It would be very, Wembe agrees with you 100%. It would be very challenged to get to that level. Bandita.
Yeah, I also agree with Musa. And specifically for me, given the research context that I'm so steeped in, it's hard for me to imagine that oil and gas is going away soon. But at the same time, I think the question of how much economic sense it makes is really, really important. And therefore, yeah, oil and gas, for a few decades at least, my personal opinion is that, and this is not like very backed up by a lot of research, I must admit, but I don't think it's going away very soon.
Absolutely. Michael.
Yeah, just the only thing I would really say on this is that one of the advantages of oil and gas is that it's very dispatchable, is I think the term they use. So you can turn on a natural gas power plant, get it up and running at a pretty high efficiency within like 30 minutes to an hour, I think. And that will always be a massive advantage that it will have over lots of other renewable energy resources, especially solar and wind, you know. So unless we have very large scale storage, you know, and fuel cell, then that's going to be tricky to have that kind of dispatchable power. So I think it'll always fill that niche. And yeah, aviation, for example, it will probably still use gas of some description, but it might be generated synthetically using hydrogen and carbon dioxide. So there will always be methane, carbon fuels, I think, being used. Yeah.
Absolutely. All right. This is our last question. We are out of time. So we are going to throw this at you. We want you to give the shortest answer you can to leave people with a really inspiring point. What's been the most inspiring or surprising thing you found in your research? Shortest answers you've got. Bandita, we'll start with you.
I think the most inspiring and most promising thing is that we're moving towards a sustainable world. Businesses are moving towards sustainability, and it's a great thing.
Amazing. Musa.
For me, it was like how much we can do with having just a little bit.
I love that. Wenbei.
For me, I think is I realized we can make a difference to the world, to the green world. Yeah.
Absolutely. All of your research is playing such an important role. Michael.
So the most surprising thing was probably just how incredibly complicated and difficult these these transitions are and these technologies are, but that's also made it incredibly interesting. And yeah, hopefully it's very cool to work out something that could be the the new technology that will maybe run the world someday. Yeah.
Absolutely. I love that. Himani.
Yeah, so I learned that, how any particular resource or energy could affect the economy of the nation by impacting the individuals who are living in those regions. So they are at the heart of the entire spectrum of the results that we are seeing. So they matter the most. So how energy affects them.
Absolutely. Whether we're working on technology, theory, social sciences, it's all about people who are underlying all of those stories. Thank you to all of our amazing presenters tonight. Catherine and I have had so much fun through this question period with you.
And we are sorry to anyone whose question didn't get answered this evening. We had very limited time and very amazing questions and amazing answers. So thank you to our speakers and to the attendees.
Absolutely. And Colleen, we'll pass it back to you.
Okay, thank you so much. Lots of information there, and I think I really appreciated the last question, leaving it on a positive note and really thinking about how big this topic is. It's really massive, but it's really important, and it requires some brilliant minds like these innovation generators that you've met tonight. So thanks so much to all of you for sharing your time with us tonight, and to our colleagues at Future Energy Systems for sharing their brains. I just want to thank you for sharing your expertise and your insight with us tonight. And to help you learn more about research being conducted by these students and the Future Energy Systems, there will be an attachment in the post-event survey that you'll receive later tonight. And there is just tons and tons of information there that you can read about each of the areas that you saw discussed tonight. Lots of other things that you can read and learn more about. So I do invite you to open up that email and check out that attachment. You'll find all kinds of additional information. Thanks again for watching tonight. We invite you or encourage you to stay connected to the University of Alberta. There are many opportunities to get involved and stay connected to us virtually. To hear all about our upcoming events, follow us at UAlberta Alumni on Facebook and Instagram. That concludes tonight's webinar. Thanks again for joining us and for supporting your University of Alberta. Good night, everybody.